Good morning, ladies and gentlemen. My name is Zhenming, and we from Team 22 will be presenting our machine learning project today. Without further ado, let's first dive into the problem statement. So, from our research, we find that young adults nowadays have financial knowledge constraints. According to Yahoo Finance in 2023, the first-time investors, the average age was 30 years old. So, to overcome this, we intend to develop a machine learning solution that can help the young adults break into the fintech or the finance world easier. So what we'll be doing includes feature engineering, such as creating technical indicators like EMA, SMA, RSI. We'll be doing model training on different models like random forest, SVM, neural networks, k-nearest neighbors. And lastly, for the class labeling, we'll have 3 different classes: buy, sell, and hold. To define each of these class, so like buy signal particularly would be if the future price like 5 days later it goes up, then it will be a buy signal today, so you can sell higher in 5 days time. If the price is predicted to drop in 5 days, then you want to sell today, so that will be a sell signal. And if the price doesn't fluctuate that much, as in not more than 5%, not less than 5%, then we call it a hold signal. With that being said, below is an overview of what we're doing today. We have data sourcing, feature engineering, model training, and lastly, some results analysis.
Thank you, Zhenming. Moving on to data source. In this project, we have utilized data source from Yahoo Finance. We have chose to focus on stocks from the tech sector, specifically stocks like Google, Microsoft, and Amazon. The tech sector is known for its volatility and high market activity, making an ideal choice for a stock prediction model. These companies are prominent players in the industry, and analyzing their stock movements can provide valuable insights into overall market trends. The dataset we retrieved includes 5 key values. Firstly, the closing price of the stock for each trading day, the highest price reached by the stock during the day, the lowest price reached by the stock during the day, the opening price of the stock, and lastly, the volume, the total number of shares traded during the day. These values form the foundation of analysis, allowing us to study the behavior of the stock and predict future price movements based on historical data. Moving on to feature engineering. This is a critical step in preparing our data for machine learning. We have selected 12 widely used technical indicators such as the SMA, RSI, EMA, and MACD, among others. These features are commonly used in the stock market to analyze price movements, trends, and volatility. These features help in identifying patterns that can indicate future price movements, which is essential for a stock prediction model. The indicators used are designed to capture different aspects of price behavior, from momentum to volatility, which are all key elements in determining stock trends. In the upcoming experiment slides, we'll discuss how these features will be utilized in different models and how their inclusion affects the performance of our prediction algorithm. Now I'll be passing my time to Tong Wei. Thank you.
I'll now be talking about sentiment analysis. So in this analysis, we aim to assess market sentiment by extracting and processing news articles related to specific stocks. So using the MarketOps API, we retrieved relevant articles for each stock based on given dates, and ensuring that only news explicitly mentioning the stock symbol was considered. This allowed us to filter and analyze sentiment scores tied directly to the stocks in question. So the sentiment extraction process involved identifying entities within each article that matched the target stock symbol and collecting their associated sentiment scores. So these scores provided by the API reflected the overall positive or negative sentiment expressed in news. To gain a meaningful daily sentiment indicator, we calculated the average sentiment score for each stock on a given day. And finally, the computed sentiment scores were integrated into our dataset, adding a new dimension to our stock analysis. I'll now be passing the time to Andrew, who will be talking about our experiments with 3 different variables, namely no scaling, min-max, and z-score. Andrew, please.
Thank you, Tong Wei. I'll be presenting our findings on optimal feature selection for our stock prediction model. We conducted experiment 1 to determine which feature approach yielded the best results. We compared 4 models, one with raw data, one with engineered features, one with random features, and one using the top 5 features identified through importance analysis. Our goal was to see which method led to the highest predictive accuracy. Now looking at the bar chart on the right, the y-axis presents our performance matrix. Notice how Model 2, using the engineered features, achieved the highest performance at 71%. Interestingly, Model 4 with only the top 5 features also performed strongly at 68%, demonstrating the effectiveness of feature selection. The raw and random feature models, 1 and 3 respectively, lag behind. We also explored different scaling techniques, no scaling, min-max, and z-score, but the trend remained consistent. So in conclusion, this experiment highlights the significant impact of feature engineering and selection on model performance. We found that both engineered features and a focused selection of top features significantly improve prediction accuracy. Thank you. Now I'll pass my time to Manesh.
Thank you, Andrew. So now we're talking about experiment 2, where we aim to identify and select the most optimal model for stock prediction. In this experiment, we utilized the RF model, SVM model, KNN model, as well as an NN model, with all the raw and engineered features being used as determined by experiment 1. Hyperparameter tuning was also performed for 3 of the models, but unfortunately could not be done for the SVM model due to our insufficient computing capability. As can be seen from our results graph, all the variations for the RF model yielded an accuracy far exceeding the other models, with the highest accuracy being 71% when features are used without any scaling done. From this, we can conclude that the random forest model will be the most optimal model in our context. Now, I'll be passing on the time to Hadi, who will be discussing the results of our next experiment, where we further aim to improve the accuracy of our model.
Thank you, Manesh. Now we will be exploring bagging, an ensemble technique that combines multiple models to reduce variance and improve accuracy. Each model is trained on a bootstrap subset of the data, and their predictions are aggregated using the majority voting. In our experiment, we used random forest, KNN, neural network, and SVM from experiment 2. The final accuracy was 56% with no scaling, 55% with min-max scaling, and 58% with z-score scaling, showing how scaling can impact the model performance. Moving on to the next experiment, which is chain boosting. The chain boosting model is a novelty technique that enhances model performance by iteratively refining predictions. This method uses models from experiment 2, such as random forest, SVM, KNN, and neural network, along with 2 key processes, residual learning and weighted averaging. Residual learning allows each model to learn from the errors of the previous model, refining accuracy step by step. Weighted averaging combines prediction by assigning higher influence to more accurate models. We experimented with the weighted averaging and found out that if we amplify the weights by cubing, we will receive the best accuracy. The final prediction aggregates all base model prediction, optimizing accuracy and minimizing errors. In our results, the boosting model with boosted model accuracy was 76.47% with no scaling, 70.7% with min-max scaling, and 71% with z-score scaling. As you can see, scaling methods had significant effect on model performance, with z-score scaling yielding the highest accuracy. Now I'll pass my time to Lin Zhenming and thank you.
Right, now we have reached the results analysis segment of our presentation. First of all, after 11 weeks of iteration and improvement, our best version of the model has achieved a maximum accuracy of 76%. Now let's focus on the 24% wrongly predicted data points. In the multi-class classification problem, there are generally 6 different cases of wrongful predictions, as shown on the right side table here. So let's examine the first 2 rows. In an actual scenario where it's supposed to be a sell signal, meaning to say that the price is at its all-time high right now and it will drop in 5 days' time. You're supposed to sell, but our model told you to buy. This is very severe as it would incur a huge loss. On the contrary, if the buy is a buy signal, meaning to say that now the price is very low and our model told you to sell, it will also incur a very huge loss. But fortunately, our model does not churn out any of these wrongful predictions. The right side table is to conclude that the wrongful predictions that our model churns out is in the manageable threshold. Meaning to say that even if the users act on these wrongful predictions, it's not that severe and it will not incur a huge loss to our users. Now, lastly, on the conclusion part, we just want to share that all these 11 weeks, we have done data sourcing, feature engineering, feature scaling, model selection, feature selection, hyperparameter tuning, and ensemble learning. And our impact, we have achieved a 76% accuracy, and to the young adults that we are targeting, they can use our model as an inference, and the risk is acceptable because the severity is very, very low. And last but not least, from Team 22, we just want to share that through our work and research over the past 11 weeks, we are confident that machine learning can aid in human learning if it's done well. Thank you very much.